Welcome to part 6 of video series on relational databases Informal Introduction. In this part, we will be talking about fitting unstructured data into relational database. And finally, we approached one of the most difficult topics for relational databases. I would even call it a painful topic. And this topic is how to deal with unstructured data. Why is that? Because it's well known that relational database is well suited for well-structured data, for well-defined data. However, we will see very soon that we can deal with unstructured data within relational database as well. Actually, term unstructured data is kind of misnomer. It's actually a wrong term because all data always have some structure, or at least useful data have some structure. If your data doesn't have any structure at all, in this case, I would say it's actually not data useful in any kind of business. It's more something like some kind of informational rubbish. So you cannot do anything if data doesn't have any structure at all. Another problem that this structure may be unknown. So better term is unknown structure. Or it could be a situation when you have highly variable structure. This is when your structure is known, but you have so many different objects, so you cannot really allocate table for each one of them. The example of that would be, for example, if you want to store in your database some big catalog of animals, and you have animals of all kinds. You have big animals, you have mammals, you have insects, and obviously they have all very different information, which has to be stored about them. So structure of data is known, but it's so big, so versatile, so you can really treat it as unknown. So better terminology is unknown structure, but as unstructured data is some kind of commonly adopted term, I will be using it as well. When dealing with this unstructured data, there is always very interesting question. Is this structure unknown to anybody in the world? So is it really unknown? Is it really a situation when really nobody knows it? Or otherwise, is it just unknown to you? Or maybe for your company, or maybe for the people you work with? So these are two very different cases, because if structure is unknown to anybody, in this case, it is so-called genuine unstructured data. In this case, the fact that they are unstructured is coming actually from the business you are dealing with. It's actually a feature of your business that you have to deal with this kind of data. An example of genuine unstructured data would be, for example, if you develop some kind of website, some web pages for social network, and you want that your members of your social network can create pages for talking about their interests. And interest of all people could be very different, and you don't know in advance what they would like to talk about. Somebody would like to have some page about landscaping, somebody will have a page about cars, somebody will have page about animals, or maybe about some scientific topics, maybe some politics. So you don't know what they want to do in advance. In this case, it's genuine structured data because it's really unknown. Now, the opposite example would be if you develop some kind of application for mortgage company. In this case, the structure of data is actually well known, at least it's well known to somebody. And the process of this mortgage approval is well defined, it's well known process, you don't need to invent it. So in this case, if you're working with such kind of project and you say that your data structure is unknown, I can only say shame on you, because you cannot really develop a project like this. You need to learn first what data structure you will have. You need to make your diligent research on this. And this is not only for the benefit of database. Your entire application depends on this. All parts of your application, all services, all web pages, whatever parts you have, they will all depend on what kind of data you have. So if you don't know your data structure in this case, you're probably not ready to start this project at all. So, as you probably already understand, I encourage you to use recommendations, which I will deliver very soon, and these recommendations will be on how to really work with unstructured data. I encourage you to use these recommendations only if you establish that you really have unstructured data. So don't use this as a simple excuse for the fact that you didn't do proper research yet. So how do we fit unstructured data or poorly structured data into tables? We know that our tables are actually well structured. Is it impossible? Actually, no, it's possible. Another problem, is it inconvenient? And this time the answer probably yes, it could be inconvenient. So if your data are really very poorly structured, and as we already established before, if it is genuine situation, so they are really of that kind, not because you simply don't know their structure, then it is quite possible that relational database is really not your best choice. But let's see actually in which situation a relational database could be still very useful. It's very often the situation when most of your data are well structured, only some small portion of your data is not very well structured. So you have only some kind of section of your data where you don't know your structure in advance, but something like 90% of your data are in well tabular format and well structured. In this case, relational database will be actually a perfect choice. I will just give you some mechanism on how to handle this small portion of unstructured data. Or situation could be the opposite, where only very small portion of your data well structured and majority of your data is structured poorly. So if this is your situation, then relational database may be not the best choice for you. Now look at those two pictures and think what picture better is representing your data better. So the picture on the left will be probably voting in favor of relational database. The picture on the right will probably require something like document-oriented database, or some other database models are available for this as well. Another important issue to establish is what is the importance of this unstructured part. It's not only the fact how big it is, what matters, but also what kind of importance it has. If you remember our previous examples, for example, we were storing data about pets of our employees. And this is example where it's probably data which are not very critically important for business. So obviously, they were just stored for fun, maybe in order to just have some information, maybe in order to send some greeting cards to people and mention their pets on these greeting cards, but this is not properly part of the business. Well, data, for example, about your mortgages, if you develop an application for some kind of mortgage company, is definitely critical part of the business. So if this data requires some different database model, is different thing. Your question is always whether this data which you have in this unknown unstructured format, is it business critical or is it just stored for some kind of miscellaneous purposes? Another important question which you will be always asking is, do you need to run queries against of this unstructured data? Or do you need just to store it, to just archive it, store it for some future purposes? As you probably already remember, the database is all about making queries, and this is actually why you would use database if you need to make queries. If you have some kind of unstructured data and you are not going to run queries, so you're not going to find some records under certain criteria within this data, then you probably don't need database at all for this. This kind of data will be better stored in file system. Or if you are using some cloud technologies, you probably can use blob storage. It's very cheap. It's specifically designed for unstructured data. So your database may be not a good choice at all. I'm not even talking about relational database. Maybe no database will be necessary for this. One of the possible implementation of storing unstructured data in relational database would be to store them as objects with attributes. This is illustrated by the following schema. we will have object table. And this object table will only store name for the object because we don't know what other fields there could be. And another column which we will store is kind. Kind will be just text explaining what kind of object it is. Is it a human person? Is it animal? Is it car? Is it furniture? Whatever it could be. And another table with very similar structure for attributes. Attributes are actually fields which will be assigned to our objects. It could be weight, height, color, voltage, whatever we want to assign. Every attribute will have name. Obviously, they all will have ID. All our tables always have primary keys. And also it will have kind column. And this kind column will be explaining what type of attribute. Is it string? Is it numeric? Is it date time? So whatever data type we want to have for this attribute. And for storing of all string values of attributes assigned to objects, we will have value string table and another table value numeric, as you probably can guess, for storing numeric values. Actually, the reason for introduction of different table is the very last column value. As you can see in the first table, this value is of type of string. And in the second table, the value type is real, which means that it is storing some fractional numbers. So I'm showing example where we can only have two types of attributes, string and numeric. If we need to support dates, logical attributes, anything else, we will simply add corresponding table to the schema. So obviously these tables are logically connected to each other. As you see, two bottom tables connected to both two top tables because they store object ID and attribute ID, which are foreign keys in these tables and which are pointing to ID of objects and ID of attribute. So, for example, the record in value string table will mean that there is some kind of attribute of type string, and it's assigned to object to certain object ID. Having this schema allows us to store any number of objects, and every object can have any number of attributes, and all attributes of all objects could be different. So in this case, we can store not only any number of objects, but also any number of object types. All objects could be different. We can accommodate something like 1,000 types, million types, whatever number of types you want. Let's now see how it works in some kind of real coding example. As always, we start from creating our tables. The script for these four tables is currently shown on the screen. Just wanted to bring your attention to data type I selected to attribute ID, which could be seen here and here and here as well. And as you see, it's small integer. So obviously integer will be too big type because we don't have 2 billions of attributes, obviously. But tiny integer will be too small because it's only 255 values and we probably would have more attributes eventually. So all done with table creation. I already executed this and I already have these tables. And now we go ahead with inserting data into these tables. And I wanted to show you that example I have selected for this is actually going to illustrate how big variety of objects we can handle. Into our object table, as can currently be seen on the top of the screen, I'm inserting 3 records. One of them is flower, called peony. Another is car, and I just named it Mike's car, just assuming that this is a car which belongs to somebody called Mike. And the third object is dog, called Tucker. So as you can see, we handle 3 objects. One of them is flower, another car, and another is dog. As you can see, there is a very big variety of objects. These 3 objects have absolutely nothing in common. Now, attributes which we will need to handle these objects. So the first group of attributes is for flower. For flower, we will be handling height, season when they are growing, petal length, and color. The next group of attributes is relevant for the car. And as you can see, we will be handling the brand, model, engine size, and some logical fields like ABS, air conditioner, and power steering. Logical means that we will store either 0 or 1. 0 means they do not have ABS, for example, and 1 means they do have it. And there is another interesting example. As you can see, we can reuse color. Color is an attribute which we added earlier for flower, but cars also have colors. So some attributes could be actually described in more than one object. They can belong to different objects. And the same happens for dog. We insert dog attributes as breed, weight, but we also can reuse height. Height was introduced for flower, but dogs also have height. And now we inserting all data into our value tables. We're describing our flower. We assign data for 4 attributes for the flower. Then we describing car, and then we describing dog by inserting the attributes. So that's all done with creating tables and inserting data. And now let's see what kind of queries we can execute against these tables. Actually, we can execute almost any type of query. Our first query will be just simply retrieving one particular object and showing all fields of this object. So it is somewhat similar to select statement for a regular table, except that we don't have regular table where we store objects. So we need to write a little bit more complex statement. As always, we start from some template, and this time it's select star from object. And we already know that from object we can select name of this object. So we'll put it already now, object name. And probably we want to know object kind, what kind of object it was. So these 2 columns are ready to go. And we already know that we will need where clause, and we will be filtering on object ID. So where object ID, in this case, it will be equal to 1. We want first object. However, this is all information we have in object table. We don't have anything else, and we want to know all fields of this object, all attributes. So they're coming from our value string and value numeric tables. Now we need to join with them. However, as you can see, we have 2 tables to join with, and we cannot make regular join. Regular join will be joined to tables horizontally by columns. We need to put one table beneath another, so we need to join them vertically. This is done by union clause, which you already seen before. So I selected, I typed this parenthesis, and this is where I will have union, which is dealing with 2 tables. And I will name this virtual table, will be returned in advance. I will name it attribute value. I will be joining this object. I need to put join. With some kind of virtual table I will write later. With virtual table called attribute value, join on object ID equal to object ID from my new attribute value table. Object ID. So this is how it will look like when we did everything with this parenthesis. And now I am ready to expand this parenthesis and put actually what I was supposed to put here. There will be 2 select statements. First select statement will be selecting object ID. Sorry for this, object ID, attribute ID, and value from our first table, which is value numeric. Let's put value string first. It's a little bit more convenient, value string. And we need to write similar statement for value numeric. I put union. I will just copy and paste this statement because it's almost the same. But this time I will be getting my records from value numeric table. It's almost done, except that we currently have type collision. Value in value string table is of varchar type. Value in value numeric table is of real type. These two types are not compatible in the same union statement, so we need to align our types. And how we do it? We convert this second value column to varchar. In order to convert column to a different type, we can use cast function. And we use the following syntax: cast value as varchar, and it was 1000, varchar 1000. So this expression, cast value as varchar 1000, means take value which is numeric and present it in its string format, presented as varchar 1000. Obviously, any numeric value could be presented in as a string value as well. So this time types are aligned, so it's all good with this. And we will want to show attribute names as well. So we also need to join all this, what we have so far, all these tables with attribute table. So in as a join attribute, and we will be joining our virtual attribute value table. Attribute value table, we will take attribute ID from this table and join it to attribute ID. So far it looks good, and now we are ready to add additional columns. We already have some joins where we can take columns which actually we wanted to show. We wanted to show attribute name and value. Attribute name comes from attribute table, and value comes from our virtual attribute value table. Attribute table value. So we're almost done here. You can go ahead and execute this statement, which I'm doing now. And you can see that I have returned my first object. My first object was flower peony. And it actually did a perfect job, except of this part. You see we have two columns with the same name, and the name is just name. We understand why we have these two columns. The first name is coming from object table. This is name of object. The second name is name of attribute. So even though we understand what it means, it creates some confusion. So if you have a situation like this, like two columns with the same name returned, it's always a good idea to rename one of them. And I will go ahead and rename attribute, name column which is coming from attribute table to attribute name. I'm doing this right now. And now I re-execute this statement, and now you see that everything looks fine. This is name, this is attribute name, and we have all information about our peony flower. We know that it has 4 attributes. It has height of 2.5, it grows during summer season, it has petal length of 2, and the color of this flower is pink. So all is done, and we can now execute the same statement for our other objects. Our other objects have very different structure. However, the same code will work. The only thing I need to change object ID. So instead of coming after object ID 1, I will put object ID 2. This is the only change. I click execute again, and now I suddenly have, as you can see, very different object returned. At this time it's Mike's car. The type of the object is car, and I have all information about this car. It's color white, it's Honda Civic with engine size 1600, and it has everything: ABS, air conditioner, and power steering. You see how interesting it was. I only changed ID of the object, and suddenly I have very different objects. So whatever was flower before now turned out to be car. And the same trick for our next object, for our dog. Just change ID from 2 to 3, and I re-execute the statement, and suddenly I have information about dog Tucker. I know the height of this dog, the breed, and the weight. So it actually illustrates that with this table structure, you can easily store objects of any kind, and you can easily retrieve them on demand. Okay, as we just have seen, we can easily retrieve object and show all information about this object somewhere on a screen or print it somewhere. But that's not really very interesting because, as you remember, the purpose of database is to make query. So previous example was just showing how to withdraw some information, and I keep repeating it. If you don't need queries, if you just need to store some information, you may not even need a database. You can select some cheaper storage like file storage. So we are more interested to learn how would we make queries against the structure. And query would be something like, give me all cars with engine size at least 1500. If we were storing this object in a separate table, we will run simple select statement. We can actually run this query against this versatile structure as well. It's simply a little bit more complex query, but let's write it anyway. So we start with our usual select statement template. We're selecting something from object, and what we will be selecting is actually object name. We need to know which object, actually which car, not which object, because we will be only looking for cars in this query. We need to know which car is passing this test. It has engine size at least 1500. So we're selecting it from object. But object obviously this object table doesn't have information about engine size. So obviously we need to join it with our value numeric table. We only need value numeric for this query because engine size is numeric attribute, and we know this. However, if we didn't know whether it's numeric or string, it's also possible to do this, and you already know that in this case we simply need to make union. So our statement will be a little bit more complex, but still possible. So join value numeric on object ID equal to object ID in value numeric table. Value numeric object ID. Now we can put our where clause. We restrict our query to value numeric value, which should be more or equal to 1500. Well, in this form, the query will work as well, but it will check any attribute, any numeric attribute for 1500. So if it is something else which is more than 1500, it will also return result. And this is not what we wanted. We wanted to check particular attribute, which is engine size. And in order to look at this particular attribute, we need to add another join. We need to join this with attribute. In this case, we will be able to look at the name of this attribute. So we join our value numeric table with attribute table on value numeric attribute ID equal to attribute ID. Once we have another table here, attribute, we can put another restriction to our where clause, where attribute name equal engine size. So this time we are not looking at any random attribute having value more than 1500, but we ensure that it's only engine size who will be checked by this query. And again, it's not complete because in this form, it will retrieve all records with engine size more than 1500, but they would not necessarily be cars. Well, in our example, we have only one object, which is car with engine size, but in real life, obviously, we will have big tables, and you should always think about your table as having something like at least million records. And there will be different objects which also may have engine size. So it's not only car who has engine size. For example, snow blower will also have engine size. Airplane will also have engine. So if we want to make sure that we follow this request, give me cars with engine size, at least 1500, not just anything with engine size 1500, we need to put another restriction here. And this time, the kind of object is stored in object table, so we need to say that object kind is car, equal to car. Well, this time it looks like we did everything what we needed, so I am going ahead and executing this query. And I have absolutely correct result. This was Mike's car. Mike's car did pass this test of 1500 because it had 1600. So this is the end of this particular lesson about storing unstructured objects. And we have illustrated that we can store objects of almost any structure and not only store them, but what is most important, we can run queries against them. We can quickly find objects which are passing certain criteria. This is the end of part 6 of video series on relational databases informal introduction. In this part, we have learned how to fit unstructured data into relational database, despite the fact that relational database is normally designed for well-structured data.